Good evening to Dr. Chong Ko Fen. Today, me and my friend will present about our assignment. Firstly, I will introduce myself. My name is Nurul Syafiqah Binti Darus. My matric number SA249, and my friend is Adzlyn Adilah Binti Idrus, and matric number SA285. Okay, first, our topic assignment is about search two scientific articles that use voltammetry and amperometry for its application. One on voltammetry and one on amperometry. And then summarize its application and explanation in PowerPoint and record our presentation in video format. Firstly, we go for application of voltammetry in lithium-sulfur battery. The lithium-sulfur battery is a type of rechargeable battery. It is notable for its high specific energy. The low atomic weight of lithium and moderate atomic weight of sulfur means that lithium-sulfur batteries are relatively light. It means about the density of water. Lithium-sulfur batteries may displace lithium-ion cells because of their higher energy density and reduced cost. This is due to the use of sulfur instead of cobalt, a common element in lithium-ion batteries. Then, cyclic voltammetry is right there for a battery. Okay, firstly, we talk about what is cyclic voltammetry. Cyclic voltammetry is almost everywhere in the electrochemistry world regarding its powerful analytic strength. Battery cannot be absent from an electrochemistry talk, as cyclic voltammetry has been widely explored for the complex electrochemical reactions and dynamics. Let's talk about cyclic voltammetry and its application in a battery. Cyclic voltammetry can not only preliminarily study the possible electrochemical reaction of the electrode system, but evaluate the reversibility of the electrode process as well as the absorption and desorption in the basic process of the electrode. Take one relatively complex electrochemical system of lithium-sulfur battery as an example. Here is to demonstrate the electrode reaction history, the compatibility of the electrode materials and electrolytes, and the stability of cathode and anode. Move to the little background of the lithium-sulfur battery. The electricity generates from the multi-electrode reaction between lithium metal and sulfur molecule. Can see that equation, that cathode discharge charge reaction, such as sulfur as the cathode has 1672 mah per gram theoretical specific capacity. The lithium anode's theoretical specific capacity is up to 3842 mah per gram. The average potential of the cathode to lithium oxide over lithium is 2.15 volt, which results in a high theoretical energy density. Then we go to how does cyclic voltammetry works. Firstly, cyclic voltammetry works by applying a potential on an electrode with scanning from EI to the negative potential direction at a rate of V. It switches to the other scanning direction when the time is equal to lambda, where the potential is the E underscore lambda, and keep scanning back the original potential at the same rate. Okay, then the magnitude of the current relies on the two steps in the process. Firstly is the charge diffusion in the electrode and the electrode reactions. During the redox process, the electron transfer coefficient is a function of the potential. You can see that equation. Then In the backscanning process, the products have a relatively high concentration and the same trend near the electrode area. It marks the current change in the same way. The electron transfer coefficient in the reverse process. The equation is at number 3. Okay, then number 4. Use the Nicholson method to calculate the current ratio from CV spectra. So, the current ratio can be used to identify the site reaction in an electrochemistry system. It also helps to identify the reaction step in the complex reaction system. Okay, next, cyclic voltammetry analytic in lithium-sulfur battery. Lithium-sulfur battery use sulfur as cathode active material, lithium as anode active material, and the electrolyte is usually the lithium salt, dissolved in ether-based solution. The separator can be the microporous polyethylene film. During the electrochemistry reaction process, there are multi-step reactions in the charge and discharge process. Firstly, in the discharge process, the anode lithium metal loses electrons and converts into lithium ion. Lithium ion goes through the electrolyte separator and diffuses to the cathode surface. Then, the lithium ion reacts with a sulfur molecule and forms lithium sulfides. It loses electrons and changes back to the sulfur molecule. Then, the lithium material is regenerated when the lithium ion diffuses back to the anode and receives the electron which is from the cathode sides by the outer circuit. However, there are supposed to generate several intermediate as the discharging products on the cathode sides. In the first step reaction, it derives two potential plateaus, which is 2.4 volt and 1.9 until 2.1 volt during the discharge process, which can be easily identified by the cyclic voltammetry spectra. Each potential generates a peak current because of the electron transfer reaction. In the multiple cycle scanning, the degree of peak overlapping from redox scanning process is useful to compare the electrochemistry reaction reversibility for different lithium-sulfur systems. Okay, next, this is the figure that show the cyclic voltammetry of sulfur in LiTFSI and PECDME electrolyte. The peak at 2.37 volt corresponds to the reduction of the sulfur molecule to polysulfides. The peak at 2.04 represents the second reduction of lithium polysulfides to lithium sulfide. The oxidation process experiences two peaks, which is at 2.3 volt and 2.47 volt. That's corresponding to the reverse reaction. Since cyclic voltammetry can be used to identify the reaction details and dynamics, it can explain the decay mechanism from the battery and discover new charge transfer or mass diffusion process inside an electrochemistry system. So next, my friend will discuss about her part.
Good evening to Professor Dr. Chong Kwok Feng. I am Adzlyn Adilah Binti Idrus with metric ID SA20085, and I'm going to present to you about the application of amperometry. But before that, I would like to explain the differences between voltammetry and amperometry. The first one is voltammetry operates under variable potential, whereas amperometry operates under a fixed potential. Secondly, amperometry is a type of voltammetric technique that is used in analyte detection. Thirdly, voltammetry results in a voltammogram, but amperometry does not result in a voltammogram. And the last one is current is measured while potential is altered in voltammetry. Meanwhile, electric current is the analytical signal for amperometry. For my part, I am going to discuss about the application of amperometric enzyme biosensors for wine analysis. Amperometry involves the measurements of currents at constant voltage applied at the working electrode. Generally, the value of electrode potential is chosen in such a way that only the metal ion is being reduced. This method is commonly used for the determination of metal ion present in aqueous solution. This analysis presents the application of amperometric biosensors based on platinum-printed electrodes and immobilized enzymes involved in wine making. So before we go into further details, I am going to show you an overview on winemaking process. In winemaking process, it includes two types of fermentation, which are glucose alcoholic fermentation by yeast and malolactic fermentation by lactic acid bacteria. There are three types of analyte present in this analysis, which are alcohol, which has important effect on the yeast growth, glucose, which being the carbon source for yeast fermentation, and lactate, which becomes the indicator of bacterial activities. This wine analysis method incorporated immobilized enzymes such as alcohol oxidase, glucose oxidase, and lactate oxidase. Now, we're going to focus on the amperometry setup and its methodology. The analysis was performed using the traditional three-electrode system in which the printed electrode combines in itself all three electrodes, which are the platinum working electrode, the auxiliary electrode, and the reference electrode. Amperometric measurements at a constant potential of positive 200 mV versus intrinsic reference electrode were carried out. The measuring condition of 20 millimole phosphate buffer at pH 7.2 were prepared for the analysis. The analysis was conducted in a 5 milliliters electrochemical cell. The wine samples were diluted before the analysis with dilution factor of 250 until 2000. The concentration of the main components of wine was determined by amperometric biosensors using the standard addition method. Next, after each measurement, the biosensor was washed with buffer solution to stabilize the basic signal. The measurement of the substrate concentrations was repeated at least 5 times for each wine sample. Now I'm going to present to you the results of three analyses using the three different immobilized enzymes. The first result is the analysis using lactate oxidase. The responses to lactate and some components of wine obtained by the lactate biosensor with lactate oxidase immobilized by electrochemical polymerization in PEDT testify to good selectivity. The only non-specific signal to ethanol was revealed for very high concentration, which never happens in wine and must. The response to the substrate is rather higher than all unspecific responses of lactate biosensor. Next, this is the results of the analysis using glucose oxidase enzyme. In the glucose oxidase-based amperometric biosensor developed in this work for glucose measurement, the enzyme immobilization in glutaraldehyde vapor was used. This is because it had previously been determined that the biosensor with glucose oxidase immobilized in PEDT demonstrated poor selectivity. The responses to glucose and other components of wine obtained by the developed biosensor illustrate high selectivity of the biosensor to its substrate over ethanol, glycerol, lactate, and ascorbic acid. Lastly, this is the result of the analysis using alcohol oxidase enzyme. The method of immobilization in glutaraldehyde vapor also was used for ethanol biosensor creation. This is due to wider dynamic range of work of alcohol oxidase that is immobilized by using this method. The study of this biosensor selectivity shows that it gave essential unspecific positive signals only to glycerol in concentration, which cannot be present in wine. So that's all from both of us. We hope that with this presentation, it can give you an exposure on how to apply our knowledge in our daily life. Thank you.